The speculation of the old endless blast is perceived by most researchers as the key clarification for the beginning stages of the universe, wrapping the formation of stars, planets, and all life, including us. Regardless of its nicely eccentric name, the term enormous detonation reasonably captures the monster of the occasion. At first, the universe was a thick assortment of particles condensed into a space more unobtrusive than a pinhead. From this moment, an immense effect of matter occurred, known as the Big Bang. This momentarily sums up the correspondence that unfolded over billions of years. However, despite the enduring nature of the speculation regarding how things became, developments in consistent data have progressively tested its assumptions. When NASA launched the James Webb Space Telescope, the greatest and most high-level space observatory to date, analysts conjectured that its insights would refine the theory of the old enormous blast. Unluckily, after only 1 year in space, the telescope has staggered experts with its vital capabilities, giving extraordinary insights into the universe's past. The James Webb Telescope's discoveries have unveiled systems so old that they might reshape how we interpret the universe's origins. This surprising openness has ignited intense interest among researchers and enthusiasts alike. One such critical revelation came when astronomer Rohan Natu, analyzing early images from the James Webb Telescope, unintentionally found a system that stunned everyone. This universe, named Glass Z13, appeared oddly gigantic and dated back to just a short time after the enormous detonation, making it older than any previously seen world. Nata's excitement was palpable as he shared the discovery with colleagues, describing it as beyond anything space specialists could have ever imagined. The James Webb Telescope, positioned far from typical interference and equipped with top-tier technology, was designed to peer into the universe's earliest age, known as the grandiose sunrise. This period, shrouded in mystery, signifies the formation of the universe's most significant stars and worlds. By examining systems from this era, researchers hope to refine their understanding of major galactic cycles, like the impact of matter and dark energy. Starting assumptions for the James Webb Telescope's discoveries were modest, expecting a few weeks' worth of distant universes. However, reality surpassed all projections. The telescope's photographs revealed systems of astonishing advancement, challenging existing models and prompting a flurry of evaluations. As experts continue to analyze the James Webb Telescope's data, the implications of these revelations could be significant, heralding a new era of cosmological appreciation. The remarkable discoveries from this critical observatory offer a captivating look into the universe's past, driving humanity's quest to unravel the mysteries of existence. As early systems emerged, scientists and spectators found themselves in a scramble to understand them. Might this assembly of unusually giant and brilliant early universes be capricious? Perhaps due to flaws in the assessment of the telescope's initial observations, or, if genuine, could they somehow be reconciled with standard cosmological models? Potentially, they're the first clues that the universe is more intriguing and complex than our boldest hypotheses had anticipated. The question remains, how do we decipher how the specific universe we know arose from the primordial chaos? The early findings from the James Webb Space Telescope could potentially enhance the foundational pieces of grand history. These regions stress distant ages in remote systems, as well as our own existence here, in the typical smooth manner. As Mark McCarran, a senior researcher at the European Space Office associated with JWST, commented, "You build these machines not to confirm the viewpoint, but to break it. You simply don't know how it will break." In a way, JWST's perspective on early universes has been billions of years in the making. However, more quietly, they trace back to the Space Telescope Science Institute in 1985. At that time, the Hubble Space Telescope was still a few years from its launch, and the Institute's then-director, Ricardo Jan, asked his team to begin considering what might come after Hubble. Shifting focus away from Hubble, Jan was relentless in anticipating the wide development process. Individual researchers, including Deputy Director of SD Sky and a small group, began drafting ideas for what would ultimately become the modern Space Telescope, later renamed JWST. They recognized that while Hubble would be groundbreaking, its capabilities would be limited by its observations in visible light. The NGST, Next Generation Space Telescope, by contrast, would see in the infrared range, allowing it to peer further into the universe. The need for JWST became even clearer in December 1995 when cosmologists conducted the Hubble Deep Field observation. Despite expectations of finding a few faint massive systems, the resulting image revealed countless worlds extending back more than 12 billion years into the universe's past. After over 20 years of development and at an expense of around $1 billion, JWST was finally launched on Christmas Day 2021. The telescope underwent thorough testing before reaching its functional space position a month later. By July 2022, it was prepared to begin its inaugural year of scientific observations, known as Cycle 1. Some of JWST's early mission was dedicated to high-impact programs, including vast development early release science surveys and the GRIS point of integration, all aimed at uncovering secrets about the early universe. As space experts devoted countless hours to scanning patches of the sky in search of early universe systems, they initially expected modest discoveries, like a more detailed version of the Hubble Deep Field. However, they were in for a shock. Stephen Balance-Lynn from the University of Texas at Austin, leading the SE project, believed that very distant systems should only emerge after several data cycles from various initiatives. To cosmologists' astonishment, these universes appeared quickly. The record for the most distant known galaxy had previously belonged to GNZ 11, seen in 2015 with a redshift of 11. Redshift measures the stretching of light due to the universe's expansion, with higher values indicating greater distances. However, from the initial set of GLASS Z13 observations, two separate teams, including one led by Rohan Naidu, independently identified GLASS Z13 with a redshift of 13, pushing the timeline back much further. In their scramble for rapid results, scientists relied on methods of redshift estimation based on brightness measurements rather than the more time-consuming direct evaluations. Despite their limitations, these estimates revealed galaxies that were unexpectedly bright and massive, some potentially boasting a mass equivalent to 1 billion suns, like our own universe. The excitement didn't stop there. Before long, additional galaxy contenders from the SINGES and GLASS groups emerged, some with redshift values as high as 20, indicating they existed only a short time after the Big Bang. These systems displayed structures that were not expected at such early cosmic ages. Moreover, another group found evidence of smooth galaxy formations at a redshift of 10, under 500 million years after the Big Bang. The rapid rise of sizable galaxies challenges the assumptions of the standard cosmological model, lambda cold dark matter, lambda CDM. To grasp this peculiarity, a brief return to early universe conditions is essential. In the early moments after the Big Bang, the universe was a warm, dense soup of primordial particles. Over time, as the universe expanded and cooled, helium and other light elements formed, leading to the emergence of the first particles around 400,000 years later. About 100 million years after the Big Bang, conditions became ideal for the formation of the first stars, made primarily of hydrogen and helium. These early stars, larger and more massive than current stars, gathered into proto-galaxies organized by the gravitational pull of dark matter. However, JWST's revelations challenge this model by uncovering massive galaxies far sooner than anticipated. Stacy M. from Case Western Reserve University noted the troubling absence of smaller, humbler proto-galactic parts, suggesting that some of these galaxies may be closer than previously believed, hidden by dust and appearing dimmer and more distant. The discovery of these early galaxies raises critical questions about the universe's beginnings, highlighting the need for continued investigation and revision of our cosmological models. Follow-up observations of GLASS Z13 in August 2022 by the Atacama Large Millimeter Array in Chile cast doubt on the initial findings. Despite the use of brightness-based techniques, ALMA did not detect significant measures of growth associated with GLASS Z13. As P. Tom B. from Goya School, who led the observations, stated, this suggests that low redshift interlopers can be excluded. However, ALMA failed to identify the galaxy altogether, illustrating the challenges of confirming observations made using JWST's advanced capabilities. Rohan Naidu, one of the researchers in question, raised concerns about the consistency of the situation, stating, "The good news is there's nothing perceived. The bad news is there's nothing related to JWST's own experiences." The most troubling explanation could be that the standard lambda CDM cosmological model requires updating. Michael Bohan-Cullen, a cosmologist, emphasized the magnitude of this potential shift in perspective, stating, "These results are extremely surprising and difficult to fit into our standard model of cosmology. It would represent a genuine upheaval to comprehend." One conditional idea is adjusted Newtonian dynamics, MOND, which posits modifications to Newton's laws to account for the observed behavior of galaxies and their rotation curves without invoking dark matter. This theory suggests that under certain conditions, gravity behaves differently than expected at large scales, particularly in low-acceleration environments like those found in outer regions of galaxies. If JWST's findings of early massive galaxies hold, it could necessitate a re-evaluation of both MOND and the lambda CDM model. The implications of these discoveries extend beyond theoretical frameworks. They could reshape our understanding of galaxy formation and evolution. For decades, astronomers have relied on simulations based on the standard cosmological model, which predicts a gradual buildup of galaxies over billions of years. The rapid emergence of large structures observed by JWST challenges this narrative, suggesting a more complex and dynamic early universe. As researchers delve deeper into the data, the need for new models that account for these anomalies becomes increasingly pressing. The debate is not merely academic. It touches on fundamental questions about the nature of the universe and the forces that govern it. Each new observation from JWST not only provides insight into the cosmos, but also invites critical reassessment of long-held assumptions. In the coming years, as further data is analyzed and more discoveries are made, the scientific community will continue to grapple with these revelations. Collaborative efforts across institutions worldwide will be essential in piecing together the puzzle of the early universe. The James Webb Space Telescope, with its unparalleled capabilities, is set to lead this exploration, offering a clearer window into the cosmos and potentially rewriting the story of how galaxies, and indeed the universe itself, came into being. As we strive to understand the origins of the universe, each finding brings us closer to answering the profound questions of existence. With new discoveries on the horizon, the journey of exploration continues, promising to illuminate the mysteries that lie beyond our current comprehension.